tangential acceleration and tangential velocity, and then what's the relationship of that. So tangential acceleration, tangential velocity, and centripetal acceleration. So kinematics of circular motion. Then we start chapter 5, which is dynamics. So kinematics of circular motion.
Can I borrow your key again, please? I wasn't there.
Huh?
Can I borrow your key just to get in? Bring it back?
Huh?
Put it here.
Yeah. Okay, so we have when something is going in a circle, we've already talked about this, the fact that it has a acceleration towards the center. So the velocity that the object has, we call that velocity tangential because it's tangent to the circle. And the centripetal acceleration is towards the center. Centripetal. And we say the centripetal acceleration is the magnitude of the centripetal acceleration is equal to the tangential velocity squared divided by the radius. So when you're squaring the tangential velocity, is almost the same thing as saying take the speed of the car and square it and divide it by radius. I know there was one question on the test 2 review that some of you got confused. It was that problem about a car going in a circle, V initial, V final, right? In the beginning of chapter 4, right? And then we calculated the V average. And then it said, what's the centripetal acceleration? And then the equation says V squared over R. So some of you thought that maybe you're supposed to take the average squared, right? V average squared over R. But it ends up that gives you the wrong answer, right? So this V is the instantaneous V. So it's V initial or V final, right? And so when you're squaring that, it's taking the speed and squaring it, not the average velocity. So it's S squared over R. If you're doing the initial centripetal acceleration, you would do the initial speed. If you do the final centripetal acceleration, you would take the final speed. And if it's a constant speed, then it's just whatever speed it is, right? So, so that gives you the centripetal acceleration. If you want to give the vector form of that, we can say A centripetal is velocity tangential squared over R, and then the direction is towards the center. So in polar coordinates, to write towards center, we write negative R hat. It's just a fancy way of writing towards the radially inward, right? And then the V tangential, we can write, if you want to write it in vector form, we can write V tangential times theta hat, right? In polar coordinates, theta hat is along the circle, unit vector along the circle, and then this is the radial vector away from the center. But you don't really need these per se. You don't need to write them that way. Then there's something called tangential acceleration, A tangential, and that happens only if the car or the object is speeding up as it's making the turn, or if it's slowing down, right? So only if object is speeding up or slowing down. So that would be the acceleration along the circle. So if the A tangential is like this, then that means the object is speeding up, right? Because it's A tangential is in the same direction as V tangential, so the object would be speeding up. So if AT and VT are same direction, object is speeding up. And if they're opposite direction, then object is slowing down. So it could happen that you're going this way, but you are slowing down, so your A tangential is like this, right? And then we can add those two acceleration vectors to get the total acceleration vector, right? So if you put this to the tip of this, you would get like that, A tangential, and then this would be called the A total vector. And then it would make, the A total vector would make an angle theta from the radial, right? If you're speeding up, then you go like that, you put that in like this, and then you get the A total, and then this would be theta. So the theta is the angle that the total acceleration vector makes with respect to the radial line of the centripetal acceleration, right? So then what would the magnitude of A total be? A total would be, have a magnitude of what? Well, then you would do AC squared plus A tangential squared square root, right? Then and then the angle here would be tangent of theta is AC, see, hold on, no, this is AT, right? So tangent theta is opposite over adjacent, and then the adjacent is the centripetal, right? So AT, tangent theta would be AT over AC, right? If you're speeding up, then the theta is positive. That means the total acceleration is ahead of the centripetal, right? So if speeding up, we could say theta is greater than 0. If slowing down, theta is less than 0. Okay? So does this happen in everyday life? Pretty much whenever you make any kind of turn, right? If you go like this, let's say a road like this, you are told as you're making a turn, usually you should be slowing down into the turn and speeding up out of the turn, right? Because you don't know who's coming from the other side. Let's say there's a car coming here. So you kind of slow down to see if there's a car coming, and then to kind of gauge your speed. And then once you know that you're going at the right speed, then you can kind of speed up again. So as you're going into the turn, you're gonna have BT, AT, A centripetal. So AT, A total is like this. Right? So as you go into the turn, the angle is going to be less than 0. Right? And then there might be a certain time where you're not accelerating, you're coasting at constant speed, and then you start to speed up. You know, now you have AT, AC, A total. And now the angle is positive, right? Okay. So if the A tangential is constant, right? If the magnitude of A tangential is constant, then you can use the equations of kinematics that we used back in chapter 2, right? If I know the initial tangential velocity and I want to know the final tangential velocity sometime later, how would I do that? Well, if A tangential is constant, I could just use V final is equal to V initial plus A tangential t, right? So even though it's not truly a linear motion, you can use the equations of linear motion. If I tell you the initial velocity of the car and then the car is speeding up, I want to know the final velocity after some time, then you can just use as if it's a linear motion, right? Then you could use the other equations too. X final is X initial plus V initial t plus half A tangential t squared, Now, see, this usually we think of as a linear motion, right? But here, x final, x initial would just be your position at the beginning of the problem, and then your position at the end of the problem. So if you subtract x final minus x initial, it just gives you the distance that you've traveled along the curve. So this minus this is the distance. V initial t plus half a t squared. And then here V initial is the initial tangential velocity. Right? And then from there you can determine the distance that the object has gone. So you can use pretty much all the equations of kinematics if the A tangential is constant. If it's not constant, then what do you have to do? Yeah, same thing that you did back in chapter 2 in a situation where A tangential was variable, then you integrate it, right? Whatever the A function is, you integrate it to get the B function. Let's see. Okay, we talked about the angle. Any questions on any of that? Maybe I can touch a little bit upon the concept of centrifugal acceleration. You've probably heard of that. Centrifugal. This means away from the center, right? So that means as you're making the turn, people that are in the car's reference frame, they feel like they are accelerating away from the center, even though they're accelerating towards the center, right? So centrifugal acceleration is actually just in the car's reference frame. So it's the perception, let's see, how should I define it? The perception of objects in the car, so that includes people in the car, right? Perception of objects in the car that they are accelerating away from the center. So it's only a perception. Why? Okay, so imagine we could illustrate this by drawing the car like this, drawing you, drawing the package next to you, then drawing the package back here, package here, and then let's assume even the doors are open, the two doors. Let's say all four doors are open, and then you're making a turn like this. You're making a turn like this, going at 80 miles an hour. That's very fast, right? So what's going to happen to those doors, and what's going to happen to you and the packages?
So
Right.
two doors are gonna tend to close.
Yeah, these two
Exactly.
doors are going to tend to close. These two doors are going to open more, even to the point where they might unhinge,
Yeah.
right? The packages, these two packages are going to slide out. This package is going to come and hit you, and you're going to feel like you're being pushed out. So you see, that's centrifugal acceleration. So by the time the car is here, this is what the situation looks like. Your head is here, the door's even more open, right? Hopefully your body's still inside. Right? This package is gone. This package is gone. No, this package may be over there, and then this package has hit you already. Okay? But the good thing is this door is closed. These two doors are closed, so you're safe. Okay? So if you want to be really safe, now do a quick turn like this. Right? And then this door, these two doors will close, and then these doors, well, since it's closed, it's not going to reopen, right? So you could do a good physics demo like that. So if you do that today, videotape yourself, extra credit, and then upload it to Canvas. 80 miles an hour, I need that.
In the rain.
In the rain, going very fast in a sharp turn. Then your friend has to videotape all that, you know. So why do objects feel like they're being pushed out? Huh? Because they're in a reference frame where that reference frame is going in a circle, and they're actually also accelerating inward, you see? But they feel like they're accelerating outward. Why? Because of Newton's first law. Objects always want to move in a straight line, right? So this guy wants to go in a straight line and wants to naturally end up there, your head. The box wants to end up here. So actually the box did whatever Newton's law wanted to do. It just went straight line, right? But because it's in a reference frame that's turning, according to that reference frame, it says, oh my God, the object was pushed out, you see? So this box wants to also go in a straight line. Oh yeah, it did go in a straight line, you see? So if you don't want it to go in a straight line, what do? You strap it with the seat belt. And the seat belt says, oh no, you're not gonna go in a straight line, you're gonna make a turn, you see? And then this guy went in a straight line, yeah, it closed. The tip of this door went in a straight line, oh, that's why it closed, you see? So it's just a interpretation, right? I think, so this kind of centrifugal idea is very, very weird. And even in chemistry, we use a centrifuge, which is a tube, right? And we put some chemicals in there and we want to get a precipitate. You want something to precipitate out. So a centrifuge is a machine that's made. You put these tubes and then they start spinning them, and then the test tubes move out. And then anything that wants to go in a straight line tends to want to go away. So the denser material is going to have more inertia, right? So it's going to tend to move away more than the liquid material. Isn't that weird? So you're really using a concept, centrifugal force, that doesn't exist. It's a false thing. You're using that to form a precipitate. You know? So you're using an unexisting force to form a precipitate. But it is kind of an existing force because in the turning reference frame, it looks like the precipitate is moving outwards when all it's doing is moving in a straight line. Odd.
Like the carnival ride is where it spins around, you can almost stand up straight because it's spinning so fast.
A carnival ride is going.
Yeah. You spin around, you can't go forward because it's forcing you back. You can almost stand up straight.
Yeah.
And gravity can't even really.
Oh yeah, exactly.
Yeah.
Yeah. And then we're gonna have a whole chapter where we do the revolution, the roller coaster rides, the physics of that. And I did a video on this, kind of cool, because weather patterns form this way too, which is why weather patterns in the northern hemisphere rotate, I believe, counterclockwise, and then in the southern hemisphere they rotate clockwise, right? One is called cyclonic and then anticyclonic weather pattern, right? And then it's the same reason why bathroom flushes counterclockwise in the northern hemisphere, southern hemisphere it flushes clockwise, and then the equator just goes down.
And this isn't centrifugal, but like the planes that they drop for astronauts to train in anti-gravity, it's a reference point, right? Because the plane's dropping, so they feel like there's no gravity, but obviously there's still gravity.
Oh, is that turbulence?
No, like, you know when they train astronauts, they take them up on a plane and they drop them really fast. So
That one actually is you are being dropped. I don't think it's a illusion.
Yeah. But,
They're dropping you so you can get used to G's.
Yeah, but like the reference point is you think you're floating.
Oh yeah, okay, maybe, yeah.
It's not centrifugal though, I know.
Yeah, I see. So here you're using the fact that in a circulating reference frame, if you even if you go in a straight line, it looks like you're going around the curve, right? I wanted to see if I could show you that. I think I might have put it in chapter 4.
This is a project one.
Well, who's that? Young,
Hey, what are you talking about? Still young, still hip. Relative. Okay, maybe I put it in chapter 6. Chapter 6. Coriolis Force, yes. This force, this imaginary force is also called the Coriolis Force.
Okay, welcome back. Now, then we'll talk about the Coriolis force and its relationship to weather pattern.
So, make it louder. This guy talks so good, we need to listen hard.
They use this in snipers.
We've heard when we were younger, we've all heard that weather patterns are different in the northern hemisphere and southern hemisphere. In the northern hemisphere, hurricanes and tornadoes, they swirl counterclockwise, right, this way. And in the southern hemisphere, tornadoes and hurricanes swirl clockwise. And also sometimes you've heard that when you flush a toilet, the bathroom toilet, it swirls counterclockwise in the northern hemisphere and then clockwise in the southern hemisphere, right? So although this is not exactly true, usually Coriolis force affects things that are larger, right? So it's more true, it's more related to weather patterns more than the flushing of toilets. Because the flushing of toilets has to do more with the inconsistencies and the way that the toilet is actually made. Right, so that kind of trumps whether you are in the northern hemisphere or the southern hemispheres. But if you have two identical toilets that are made exactly the same, they don't have any inconsistencies, no dirt on them, nothing accumulated near the sink, then it is true that toilets in the northern hemisphere or sinks in the northern hemisphere will swirl counterclockwise, and then toilets and sinks in the southern hemisphere will swirl clockwise. So you're going to see this. So the Coriolis force equal to negative twice the mass of the object times the rotation of the rotational angular velocity of the object, of the surface that you place it on, cross product with the velocity of the object with respect to that rotating object. So the way that the Coriolis force is made is that you get an object rotating like a platform. So in my case, I'm going to have a platform like this, and I'm going to get it rotating counterclockwise or clockwise, right? So that if I get it going counterclockwise, you get your right hand and you curl it in the direction of the rotation of the object, and your omega vector points up, right?
So a bit of Calc 3 right here, right?
And I start the ball over here, right? And I push it inwards, right? Inwards, radially inwards. What will happen? So the direction, basically you can think of it this way. This is a 3D picture. The direction of the velocity of the object is into the board, right? This way. And the omega vector is up. So then this equation is saying, take the omega vector and cross product with the v, omega crossed into v and u, right? And the negative of that is going to give you the force, negative 2 and omega crossed into v. Okay, so if that is true, what's going to happen as this thing is going into the board, it's going to feel a Coriolis force that way. Coriolis force. So basically the Coriolis force is in the same direction as the rotation of the object. So if it's rotating like this, the Coriolis force is in this direction, but in the meantime, the object is traveling like that. So when an object travels like that and you exert a force on it like that, its path looks like this. Its path goes like this, like that, swirls around, right? So if this is spinning fast enough, you could actually get this to go like this and spiral back, and that's how a hurricane is made, right? If I go
In other
very
words, if I
fast,
throw
then
this
it's gonna go like this
slow,
and fall off the
then it's
table,
gonna go and
right?
curve
So it's
around.
just gonna go like this, curve, and then fall off the platform, right? But if I go very slow, and if this is spinning fast enough, and you might cause it to actually go around, so it will actually go counterclockwise like that.
Beautiful.
Okay? So now, if I get it spinning the other direction, right? Like this. So now, let's say it's spinning this way. Okay, like that. So
do the
now,
right-hand
the
rule.
omega vector is down. Right? Omega is down. And let's say I push it inward. Okay? I push it like this, inward again. So then the V is into the board, omega is down. Omega crossing to be this way. We take negative of that, so that's going to give you the force, right? So this time the opposite is going to happen. The object is going to go like this. The object is going to go like this, and then it's going to curve this way. So this is exactly why weather patterns are counterclockwise in the northern hemisphere, but clockwise in the southern hemisphere, right? Because the way that the Earth rotates,
Now I'm going to apply this to the
way that
Earth's
the
weather
Earth rotates,
pattern.
it's like this. It rotates like this, counterclockwise. So in the northern hemisphere, it's like being on a platform that's rotating counterclockwise, right? But in the southern hemisphere, it's like you're basically right side up like this. So in the southern hemisphere, the opposite is true. You've got to go like this, and if an object is rotating like this, but if you view the bottom go like this, then it's actually clockwise, right? So the Earth is rotating counterclockwise when viewed from the top. But if you view it from the bottom, it's rotating clockwise, right? So if you're living in the southern hemisphere, you should be saying the Earth rotates clockwise, okay? If you're living in the northern hemisphere, it rotates counterclockwise. So let's see the video, and then you can get a better understanding of how this works. Okay, so then I can kind of start spinning this counterclockwise like this. Okay, get a ball going like this. Throw it inwards. You see its path? Okay, let's go again. Go like this. Okay, so you see how the path went like this? But then the reason also it falls off is that there's not much friction between the ball and the table, and it just kind of falls off eventually. Okay, what if I spin it clockwise?
Oh,
Nice. It went like this and went clockwise, then came back. So actually, it made a full circle before falling off. So there is your hurricane pattern in the southern hemisphere. Okay? Let's try that again. Okay, now I hope that the video has helped you kind of clarify a little bit more about how this pattern is developed. So even though the object is traveling in a straight line with respect to the table, but because the table is rotating with respect to us, that causes the overall path of the object with respect to us to look curved. But the path of the object with respect to the table is straight line. You see? So Coriolis force is almost kind of like you can think of it as an imaginary force caused when you are on an object that is rotating. You might be traveling in a straight line, but because that object is rotating with respect to another reference frame, there appears to be a force on you with respect to the stationary reference frame, which is making your overall path curved, right? So then this is how the weather patterns are created. Now, if the Earth wasn't rotating at all, how would toilets flush? How would weather patterns form? Not really, right? They might form just due to their internal motion, but they're not going to be as strong at all, right? On Jupiter and Saturn, weather patterns are a lot stronger because the rotational speed of the Jupiter and Saturn are a lot faster. They rotate once every 10 hours. Jupiter is the fastest rotating planet, so we would expect that weather patterns would develop much more easily on Jupiter. First of all, because it's a gaseous planet, it's huge, it's very massive, and plus its rotation is very fast. So the Coriolis force effect is a lot more because the omega of Jupiter is a lot bigger, and it's going to cause a lot more force, a lot more rotation, and much bigger hurricanes. Okay? Thank you very much.
Now, if we look at this car's motion as almost like a Coriolis effect, can we interpret it as almost like that? Instead of saying centrifugal force, can we say that the person in the car is experiencing Coriolis force? I think we should be able to. They're probably just interchangeable,
I know.
right? So imagine, what was the equation for the Coriolis force? The force on object is equal to negative 2m omega crossed into v. So what's the omega? The car, imagine the car is the thing that's making the turn. So what direction is omega? Do your right hand rule, the omega is into the board. What's the direction of the velocity of the person? This way, or we could say this way, depending on if we catch it here or if we catch it here. So let's just say we catch it at the top, the velocity is like that, right? So now what's omega crossed into v? Omega crossed into v down, but negative omega crossed into v up. That is the Coriolis force. So the reason you feel an outward push, the reason the doors close and some doors open, you're experiencing the Coriolis force, brother.
When you say omega crossed into V, what do you mean by that?
The omega is the radial velocity of the surface that you're, see, imagine this is a platform that's rotating like this.
Mm-hmm.
So the omega is a vector that if you do the right hand rule, you curve it in the direction of the rotation.
Yeah.
The thumb points in the direction of the omega. And omega is units of radians per second.
Okay.
And then velocity is the direction of the person is trying to go, which is this way, this way, this way, like that. That's you. So that's going to be meters per second. So what is that going to be? Meters per second squared, right? Meters times radian is just meter per second squared. Times kilogram is going to be what? Newtons. That's the Coriolis force.
This is why I always heard like Coriolis effect. Only time I've heard that is like long range snipers. They have to know which hemisphere they are in because
Exactly.
it won't hit the right spot.
You won't hit the right spot. So not only you have to worry about air friction and all of that, but also the curvature of the earth. Yeah. So now, so every time you're actually in the car making any kind of turn, you're experiencing a mini hurricane effect.
So Newton's first law correlates with Coriolis.
What is?
Newton's first
It's
law.
Newton's first law that's causing the Coriolis effect, because you want to go in a straight line, but you're in a reference frame that's turning,
Yeah.
right? So what happens for the weather patterns? What happens for the weather patterns is that, see, imagine this as a platform that's turning like this. So the Earth spins this way, right? And then usually the seas at the equator is warmer than the seas at the North Pole, right? So this heat, the ocean at the equator gets hot, the heat rises and then starts wanting to move towards the North Pole, and then the heat here warms up and starts moving towards the South Pole, right? So imagine an air pattern going that way. So the velocity is this way, right? Let's see here. .3D. I have to try to visualize 3D.
Yeah.
I'll come back to you on that one because I want to apply it to how the weather pattern
So
circles.
you're saying it's like hotter in the equator, so that hot air rises out of the core.
Yeah, so hot air rises out of the
But-
surface of the water and then begins to want to move towards
Yeah,
the.
so it's curving because of that, and it starts to.
Yeah, and then so as it's going this way, the Earth is spinning.
Yeah, and
So try to visualize all of that 3D, right?
so like instead of a hot line of air and a cooler
So
line
instead
of
of a
air,
hot line like going like
It
this,
starts to
instead of going
curve
like this,
and-
it goes like this. You see like
and
that.
it creates the.
Yeah, there you go.
Yeah. Okay.
Yeah, exactly. Going like that.
Yeah.
I'm trying to do it in terms of the omega crossed into V, and I got stuck for a sec. Yeah.
So when you're turning, you're on a car and you're making a right turn, how does that correlate with like the Earth spinning?
Oh no, I'm not even applying the Earth spinning. You're in the car, so the car is the spinner. The car becomes like the Earth.
Yeah.
It has nothing to do with the Earth spinning. The Earth could be stationary, and you could be in a car making a turn, and you'd still feel the Coriolis force.
So what was omega cost of? Well, what's the cost of omega?
Cross product?
Yeah.
It's the cross product is the cross product between two vectors. It's a right-hand rule.
Yeah, but so omega is a cross between which vectors?
No, the cross product is between the vector omega and the V.
So how do you find omega?
Omega, you do the right-hand rule. You curve your fingers in the direction of rotation of the platform, in this case the car,
Omega,
and omega is
kinda
into the
like
board.
thumb,
It's the
right?
thumb. The
It's
thumb is the omega.
direction of your thumb. And then for the cross product of omega and then V, it's kind of like you're doing like this way.
Yeah, for the
Yeah.
platform, the
That's
video
right.
that I had, how was it? The platform was rotating like this, and I set the ball inward, right?
Yeah.
And then it was like this, like that. So omega was like this,
Yes. And then for omega and V,
and then the V was into the board, right?
Yeah.
So omega crossed into V,
But it's opposite.
but then negative of that. So you can kind of see why it went like that. But if I had done the opposite, the ball started from the center coming outward, what would have happened? Right? Ball starts at the center and then I push it out. So then the V would come out of the board towards you. So it'd be V cross into, then it'd be like this. So it'd be the opposite, the force. Right? So if it was coming outward, what would the path look like? Let's look at a top view. Coming out of the thing, what would it do?
Go counterclockwise.
Basically, the force instead of being to the right, it would be to the left.
Oh.
yeah, right.
So it's gonna go, and then maybe just curve like that. Yeah. So basically, it seems like it curves in the direction of the. Oh, let's see here. No, it actually curves.
Shouldn't be going there. Because you're gonna pull and
V is this way. Omega is out of the board. Omega crossing to V. Yeah. So omega crossing to V is this way, so it goes like that. It depends which view you're looking, side view or top view. Side view, top view is different.
Oh,
Right.
is this side view?
This is side view, this is top view.
Oh, okay.
This is top view. Go like this. I throw the ball away from the center, and then the thing is going like this. So which direction is omega? Out of the board. So now do omega cross into V, then flip it. So the force it experiences is like that. So it's gonna go like this, and if the thing is spinning fast, oh, so it's actually gonna spin opposite to the rotation of the platform.
Opposite.
Really?
Here it spins same direction as the platform.
Yeah, it should be opposite.
Here it's opposite because it's coming away from the center.
Yeah.
Ah. So it depends if the weather pattern is going from the North Pole down to the south. It's different than if it goes from the equator to the north. You see? But usually it should go equator to the north, right? Because waters are warmer in the equator than the North Pole. Yeah.
So can I conclude that like omega is kind of like the centripetal acceleration, the cross product of centripetal acceleration and then the velocity, that's omega, and the force, right? That's omega.
Omega is
The cross product of acceleration and the velocity.
yeah, I mean probably, but I don't wanna dwell too much on the cross product right now.
Yeah.
I mean,
Like that inside. So that's omega.
yeah.
And the force is omega. And
Exactly.
velocity.
But the whole idea was that we can interpret the centrifugal acceleration as an effect of the Coriolis force.
Because it
That to me was the surprising thing.
It just matches up with the direction.
Exactly. Okay, let's do one example of this. A car is going see, based on this, what could I ask here? What is the radius of the turn? So, what is the radius of the circle? What is a tangential? So in this one, I've given you pretty much nothing about the circle. Like you don't know the radius of it, but only that you know that at the instant that the velocity is that, at that instant the acceleration is that, right? So let's try to draw a picture and see what is happening. So, the other thing, you know that it's going clockwise. So where do you think the car is along this circle, according to the problem? If it has a velocity 3.8 and 2.4,
The top left.
it's going clockwise? Yeah, because clockwise determines the direction of flow of the car, right? So only at this top left can its velocity be both positive and positive, right? And is it closer to the x component is larger, right? So if the x component of the velocity is larger, is it closer to this side or this side? The top, right? Okay, so it's probably somewhere there. right? Because the x component is larger than the y. So the car is somewhere there. That's all we know because we know it's going clockwise. Okay? We know the total acceleration vector. It has a y component that's larger than the x. Let's see. So the total acceleration looks like this. Well, that doesn't make sense. I don't think you can have that. The two need to match. Let's see. I think this one needs to be negative. Yeah, it doesn't match. It's an impossibility. That would make sense, right? So that means the total acceleration looks like this. It's something like this, and then, right? So it's something like this. X. So I see, when we say it's 4.2, what does that mean? That means from here to here it's 4.2, and then from here to here is negative 8.6. Measured from there, right? And then, so that means the acceleration vector looks something like this. So is this car slowing down or speeding up? I don't think I can tell yet, because I can't tell if the acceleration vector is it along the centripetal line or is it ahead, you know? From this I can't really tell.
Can you just quickly explain again how you use the velocity vector to determine its position?
Oh, because I knew that the x component of the velocity from here to here is 3.8, and then from here to here is 2.4. So the only place it could be both positive is if the car is there
Oh.
and it's going
Oh, I
clockwise.
see.
Yeah.
How did you find the?
That's the acceleration vector.
The acceleration. Does that answer your question?
Acceleration vector. No, that's velocity. He's asking about acceleration.
Oh, acceleration is 4.2 negative 8.6. So it's 4.2 negative 8.6. I don't really care 4.2 and 3.8 when I'm drawing it. The 4.2 doesn't have to be larger than the 3.8 because they're different units. But what matters is the ratio of 4.2 to 8.6. This is about double that size. So the vector, the acceleration vector looks like this. Is it facing towards the center? Well, we don't know. Is it facing ahead of the center or behind the center? So what should we do to determine all that stuff? Well, let's determine the angle of the velocity vector, theta, right? Because velocity vector is always tangential to the circle, right? So then we can do 24 over 38, and then 12 over 19, and then take 10 inverse of that. Pretty interesting problem here. A lot of visualization involved in this to visualize what is happening. So, what is that? And then while we're at it, we can get the magnitude of the velocity because we're going to need that anyway. Which one?
The vector going first.
No, this is the total acceleration.
Oh,
Because they told us the acceleration vector is that. Well, if it's not specified a tangential, we assume this is the total. Because they told us the acceleration vector is that. Now they're asking us what is the a tangential and what is the a centripetal. Okay, so what are those numbers? Huh? 36.2. 0.28. Okay, this one. Huh? 4.49 meters per second, right? Okay, now, if that's 32.28, that means this is 32.28, right? So from that, can I find out if I draw a line from the center of the circle? Let me draw something like this, a little bit bigger. Let's say the center of the circle is here. So if I draw a line from the center of the circle to there, right? So this line is tangential to that, right? So V, this is 90 degrees, right? So if this is 32.28, this is 90 minus 32.28, right? This is similar to that problem on the first test review, the first one, right? This is 90 minus 30, and then this is also 32.28. Because these are all 90-degree angles. This one, this one, this one, 32.28, 32.28. So now if I want to find out the A that we have is 4.8 and negative 8.6. Well, why don't we find out this angle of the A, right? Let's see what that is. Tangent inverse of negative 8.6 over 4.2.
What makes those the same triangle?
Because that's velocity, good question. He's saying what makes those the same triangle? Because the velocity is always tangential to the circle, which means if I draw a line from the object to the circle, this angle is 90. Always. You see? So if I draw that again with less clutter, this is the center. So this is 90, right? So if this is 32, this is also 32. Yeah. So now I'm trying to figure out, this is the acceleration vector that we have, right? The total acceleration vector. I'm trying to figure out this angle. Let's see what that is. What do you get? Negative 63 point. Huh?
97.
So what does that mean? So now we can determine if the acceleration vector is towards the center, this way, or behind it. You see? If it's behind, then it's slowing down. Car is slowing down. See? So if this is 63, what would this angle be? 90 minus 32. Huh? Oh, so that's 68. Woo! Wow, deep. So, wait, no, 90 minus 32 is 58.
Less
Oh,
than 60.
so 58 point what? 58.52. Oh, hold on. This minus 90?
57,
57.72.
72.
Oh yeah, okay. So that means 63 makes the acceleration look more like this. This is 63, right?
That's 8.
Huh?
Yeah.
So what does this make this small angle? 63.97 minus 57.72. And that's this small angle. That's the angle that a minute ago I called tangent theta is A tangential over A, what was the equation? It was the angle measured from the radial line, right? A tangential over A centripetal?
Yeah.
Yeah, that's that angle, the small angle that the total acceleration makes with respect to the radial line, right? So that angle is the angle theta. So 63 minus 0.97 minus 57.72 . 6.25. 6.25 degrees. Okay, now from there, can we calculate the centripetal acceleration and the tangential acceleration? See what I mean? This thing and this thing. Right? Yeah.
Where did the 57.72 come from? Like what part, what part of it?
57.72 came from.
Like what part is that?
Oh, that one was the 30. Let's see. The velocity was given, right? 32.28. I subtracted 32.28 from 90. That give me, this guy was, from here to here was 57.72. And then this thing was 63. Okay, now let's, if we have the tangent theta, 6.25, how can we find out A tangential, A centripetal? Oh, we also know that A centripetal is equal to V squared over R. Great. Okay, we know V squared is what? 4.49. Oh, but we don't know the radius, right? Do we have too many unknowns in this problem? 4.49 squared over, but we don't know the radius.
That's the first thing you're trying to solve for.
Huh?
That's the first thing we're trying to solve for.
Yeah, we don't know the radius, so I'm trying to determine if this question has too many unknowns or does it have enough information for us to solve it, you know? And then the next thing we know is that the total acceleration, A total is equal to what? Square root of AC squared plus A tangential squared. And we can determine the total acceleration, this squared plus this squared, right? That is the total. So A total, we can square this. So this guy, A total squared, is actually 4.2 squared plus 8.6 squared. That is A total squared. AC squared you don't know, A tangential squared you don't know. Oh, we could solve it. We have enough information. And then here we have tangent of 6.25 is equal to AT over AC. Can we do a substitution? We can say AT is equal to AC tangent 6.25, right? Substitute that into AT. Beautiful problem. Ooh, nice. And AT is equal to AC squared tangent 6.25 squared, right? So 4.2 squared plus 8.6 squared is AC squared plus AC tangent 6.25 squared. So then how do I solve for AC squared? I can factor out the AC squared, 1 plus tan 6.25, tan squared, 1 plus tan squared 6.25. Right? Is that it? Because I'm only squaring this, right? 1 plus tan squared is equal to secant squared, isn't it? Right? 1 plus tan squared is secant squared, which is 1 over cosine squared.
How did you get 1 plus 10 squared?
Because tangent squared. AC squared, tan squared.
Yeah, but the products.
Yeah? Two numbers product squared is each one squared.
Yeah.
Then you can factor out the AC squared, then you get 1 plus tan squared.
Oh, okay, sorry.
Yeah. But it's okay, always ask. Then you got secant squared, then 1 over cosine squared. Right? Then I can square root everything. Then what's going to happen? AC equals cosine 6.25 square root of okay, from there we can calculate a centripetal. Oh, I went through a process of arguing that this is secant squared 6.25, and then I said that's 1 over cosine squared. Then I square rooted it to make it the simplest form.
Where do you get the 6.25?
That one was the difference of the 63.97 minus 57.72. And that's this little angle. Then what? So this gives us a number, right? What is it?
0.5, 0.27699.
0.5, 0.
276,993.
Okay, so that's a centripetal, right? From there is our key to determining the radius of the circle. A centripetal squared, a centripetal is equal to what? B squared over R. So a centripetal is 0.5027. B squared is what? That's your 4.49 squared. And that gives you the radius of the circle.
For the tangent, inverse negative 8.6 over 4.2, you get negative 63.97. So you just disregard the negative.
Well, no, just the negative just means that it's down. That's all, which I already did it. It's just below the x-axis.
So the acceleration vector has a positive I component, so what does that mean for the
Positive I? Yeah, no, it's still going to the right. Oh yeah, very good question. He's saying the acceleration vector is has a positive I component, yeah. It's still moving to the right from the x-axis.
Oh, it's just in a direction.
It's just that it's directed behind the radial line. Yeah. This doesn't mean it's going to the left. It's going behind the radial line connecting the car to the center of the road. See, the car could be here. This is the radial line, right? And it could go like that. It's still moving to the right, but it's behind the radial line, so the car is slowing down. You're never gonna make turns any differently from now on, right? You're gonna visualize these vectors.
Where if the angle was smaller, then it would be on the other side of the road.
Then it would be other side, that means you would be speeding up. Yeah.
Yeah, I was gonna say that. So
What is it?
Yeah,
For
9.5.
a centripetal?
Yeah.
9.514. Yeah, you should, because this is a large number. Cosine of 6
Yeah.
should almost be 1. So my alarm bell should have already rang. Jing, 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 right? So, yeah, but I did it on purpose so that you guys, right? 9.514. So now you have here, so, oh, radius is very small. 16 over 9. What is that?
Sorry, we're drawing.
2.16 meters. Huh? Huh? 2.12. So that means it's a very sharp turn. Radius of 2 meters. Oh my gosh, very sharp turn. But the car is going very slow, also 4.49. So it's like a really, it's more like a bike basically, you know, or it's a person running. Okay, so what else? Oh, we're left. The only thing left to do is the tangential acceleration. A tangential is what? Then we can just put it here. A centripetal tangent 6.25. That's of course the magnitude of A tangential, right? So that's the rate at which the car is slowing down. So that should be a small number, right? Because tangent of 6 is, yeah, tangent of 6 is small, right? You can almost put negative 1.04. Why? Because the car is slowing down, right? Slowing down. Okay, now can we go, let's see here. Assume the car had been slowing down at the same rate for a while. Tell me where the car would have been. So imagine it's slowing down at this rate. And it has been slowing down at this rate for a while. Tell me where the car is 5 seconds earlier than this. Where the car is, what is its velocity vector, and what is its acceleration vector 5 seconds earlier. So assume the car had been slowing down for a long time at the same rate. Find out the position of the car velocity of the car and the acceleration of the car 5 seconds earlier. So it's kind of like you're doing a continuation problem now. So the car's probably be somewhere here, right? 5 seconds earlier, or it could be that it's here. Just like take the clock backwards. Remember, if the acceleration is constant at that rate, what can you use? You can use the equations of kinematics to determine what its velocity would have been earlier, right? What its speed would have been, where would it have been, right? So use those equations of kinematics. So now you guys work on it. Yeah, just go backwards in time 5 seconds. So where is the car? What is the velocity of the car? Yeah. You guys want me to start you out? Are you like lost? Are you lost? Like, how do I go backwards in time? Is that scaring you? Remember, you can go backwards in time. It's just find the wormhole, take the car backwards in time 5 seconds. Right? Here's what how you're gonna start. You're gonna say, speed final was, what was the final speed that we had? 4.49, right? Initial speed, and then negative 1.04, and then this is 5 seconds. Right, so that it's decelerating at a rate of 1.04, the car. That's a tangential. The final speed, when we started the problem, remember the velocity was 4.49? So what would the initial speed have been? 5 seconds earlier.
You can just use
What
5.
if the tangential velocity was faster? What if the acceleration was lower?
No, we're assuming, remember what it's saying. Assume the car had been slowing down for a long time at the same rate. We're assuming the car's braking at the same rate. So a tangential is not changing. Its direction is changing, but the magnitude is not changing. Right?
So it's the 1.04 is negative because it's slowing down.
Because it's slowing down. That's how we determined that it's slowing down, right? Because it was back. So assume the car had been slowing down for a while, then we can go backwards in time and say, oh, 5 seconds earlier it was going faster.
Well, I think you could use that velocity to find the
Well, now you know the velocity that it's going at, right? So now from there, we could also find the distance that it traveled. The initial is 9.69 times 5. Right, so if the initial velocity that it started 5 seconds ago was 9.69, and it is decelerated at 1.04, that's the distance that it would have traveled, right, in 5 seconds. So that tells you the distance it would have traveled. Then once you find the distance, you start working backwards, find out where the car is along the circle, because we already know the radius of the car, right? So you work backwards to find, so what's the distance here? So get the distance divided by the circumference of the circle, right? Determine where the car is from there.
When you're calculating the final velocity, since our starting point is over here, still use 5 for time?
Yeah, because it's 5 seconds. Long,
But it's 5 seconds
find
before.
out the R 5 seconds earlier.
So wouldn't that? Oh, okay.
The acceleration is negative 1.04, 5. So 5 seconds earlier it was going faster.
Oh, the initial. Oh.
Initial
Yeah,
speed
yeah,
5 seconds earlier. Okay, you determine the circumference of the circle and then determine the distance. What's the distance? 25 over 2, 12 and a half. Oh, the distance is quite a bit. So what does the distance come out? 35.45 meters. So what's the circumference of the circle? Divided by the circumference 2 pi r, and then 2 pi, what's the radius? 2.12. That will tell us how many turns it has made in those 5 seconds. This is 4 times 12, 35 over 12, about 2 point something, huh? Okay, so now in 5 seconds, it's like taking this movie backwards. The car is here, 1 revolution, 2 revolution, and then 0.6 revolution would take us where? From here to here is a half of a revolution, right? So 0.6 revolution is probably somewhere around here, right? Opposite to it, but a little bit more than opposite. So the car is here, moving this way. Somewhere over there, moving downwards because it's going clockwise, right? So that's where the car is 5 seconds earlier. How fast is the car going? 9.69 meters per second. Can we find out this angle from the car's position? Right, so this is the distance, 2.12. Could we find out this angle? How?
Like taking
Yeah, so do the 2.661 turn. This is turns. Forget about the 2,
points.
right? Because we just went back twice already. 0.661 turns times 360 degrees. 0.661 of a turn is how many degrees? So then you multiply by 360, it's over, a little over 180 degrees, right? So what is that? 0.661 times 360. 237 point. So that means this angle, 237.6 degrees. Okay, from there we could determine this, right? Because we know its original starting point was 32.28, right? So we could determine this. So what's this angle now? If I do 32.28 plus 237, that gives you this whole angle. Then you subtract that from 270, right? So you're applying a whole bunch of geometry and trig here. $32.28 plus 237.6. That gives you 269.88. Whoa. It's almost 270. This plus this is almost 270. Well, so that means the car is almost about here. 269.88. So this whole angle is 237 plus 32, so that's 269.88. So that means this little piece is what? $270 minus that, which is 0.12, right? Right? Now, we can say, okay, we know the position of the car. It's going downwards, and this is 0.12 degrees. Oh, it's so small. Huh?
Wouldn't it be like 3 though?
Did I have it wrong? Hold on. 290, 180, 27.
No, it's going clockwise.
Huh?
It's going clockwise.
Yeah, so I went backwards.
never
This
mind.
is 1, 2.
Yeah, you're right.
Yeah?
Yeah.
Okay, so if that's 0.12 degrees, isn't this also 0.12 degrees? Right, the velocity makes a 0.12 degree angle from the y-axis, right? So now we can write down what the velocity vector is. This velocity vector in the I-hat direction and J-hat direction. What's this gonna be? The x component. The x component is gonna be this little piece, right? So what is that going to be? 9.69. The sine of 0.12. Sine of 0.12. So opposite. Right? So it's a very small, because pretty much the car is almost going down. So velocity is going to be 9.69 sine of 0.12, but negative. Why? Because it's going to the left. I hat. How about the J direction? Minus 9.69 cosine of 0.12 J hat. That's your velocity vector. Your faces are like all yellow, just your heads are spinning. You guys are experiencing the true Coriolis force of physics right now. So it's a small negative number, but almost 9.69 here, right? So Okay, how about the acceleration vector? We have a centripetal, right, towards the center, and then a tangential is going to be what? This way, because the car is slowing down at 1.04, right? A centripetal is going to be facing this way. When you add this vector to that vector, what are you going to get? A total is going to look like this. So the A total vector should be some negative number plus some positive number, right? Left and right, up. Okay, can you guys finish that? What's the A total vector gonna be? So I've already given you the position, I've given you the initial velocity. You know the A tangential is 1.04. So combine A tangential to A centripetal. Wow, can you fit that in that small paper? Your papers are getting smaller and smaller. Next, you're gonna write on
Because that's the last notebook.
Okay. Well, there's no
there
equation
one?
for it. No.
It would be just the instantaneous velocity.
A tangential is the rate at which the instantaneous speed is
But
decreasing.
AC would just be tangential.
Yeah, exactly. Squared over r. Yeah. A centripetal has an equation, but not a tangential. But you already know a tangential. We figured it out because it was 1.04.
Oh, that's,
Yeah, that's
okay,
constant.
okay.
It's basically like doing the sum of two vectors, right? Find out the A centripetal magnitude, break it down into components, find out the A tangential magnitudes, but figure out its components, and then add the two components, and then tell me what you get here. I'm gonna do the answer, I'm gonna try to do the answer in my head and then put it here. And let's see if anyone else gets the same answer. answers I'm getting. Okay, that's what I'm getting. Negative 44.2883 I hat plus 1.1328 J hat meters per second squared. Right, Alan? Getting the same thing?
So, how do we get this?
That's for you to find out. Some things are left as mystery, right?
So,
Work in groups, guys. Figure it out. Put it on Canvas in the discussion, the general discussion board I have on Canvas. Say, hey, this is how he got this answer. I figured it out, and put your solution there. That's what that discussion board is there for. So you guys can put solutions of problems. Right? Okay, guys. See you tomorrow in the lab.